Hi guys, I just wanted to show you something further with index laws that you've been doing. Now this is technically an index property or an exponent quality. It's not technically a law, but we still call it the law of equality of exponents, and some other people call it slightly different laws like the law of equal exponents or something like that. But it's still a really cool property. And what it says is that if two powers with the same base, and that is really important, are equal, then the exponents are equal, but only if they have the same base. So that means, for example, if we had like 2 to the power of 5 equals 2 to the power of x, then this law of equality of exponents means that therefore x equals 5, which makes sense. In order for them to equal, they would have to have the same power there. And we can use it to get a little bit more complicated. So for example, if we had, let's pick another number, 3 to the power of 2x equals 3 to the power of 6. And that would mean that, remember this is the therefore symbol, the 3 dots. That would mean that 2x equals 6, and we know from algebra that if we want to find x, we have to undo what we've done. So we would divide by 2 here, and divide by 2 here. The 2's would cancel out, and we'd end up with x is equal to 3. And we can get more and more complicated and more complicated. So we could do, let's do another one. We could have, let's go 5, 2x minus 1 equals, let's say, 5 to the power of 3. So in this case, we'd go, therefore, 2x minus 1 equals 3. We know to undo that we'd have to go plus 1 here because we have to reverse the order of operations. So plus 1 here, and we'd have 2x equals 4, and then we'd divide by 2, cancel those 2's out, divide by 2 on the other side, and we'd have x is equal to 2. And that's how I can use it. The issue we come to is if we have something where they're not the same base. So, for example, what if we had 4 to the 2x is equal to 2 to the 4. And that's when we have to do something else. So if we have two different bases when we're wanting to use this law of equality, and we have two exponents, and we want to find out what that x is or what that a is or any different variable, we can actually change the base. So for example, if we have a 4, we know that we can make 4 out of 2, can't we? We know that 2 squared is 4. So if we had, let's say, 4 to the power of 3, and I wanted to change this into a base of 2, and I don't know what power it would be. So what we do is we use our index law. Remember that we learnt yesterday, and we touched on it last year as well. We use our power to the power rule. So remember when you have power within the brackets. So for example, let's just use a. So if we have a to some power, let's use 2. And then we raise that to another power, let's use 5. That would be the same as a to the power of 2 times 5, which would be the same as a to the power of 10. So we know this rule, and this is why this is an extension activity, is we're actually going to use this rule in combination with this one. So instead of writing 4 here, I'm going to write 2 squared in brackets. But remember, that was our 4, and we've got 4 to the power of 3. So we have a 3 there. And I can use my index law here. This is law 4. I call it the power to power rule, but the textbook calls it the raising the power rule. Either one is fine. Or to the power. And so we know that we just multiply that through. So we have 2 to the 2 times 3. Now again, this is the optional line of working out. You don't have to show that one, but you do have to show some working out. So we do need to show this one. So 2 to the power of 2 to the power of 3 equals 2 to the power of 6. So now we know 4 to the power of 3 is the same thing as 2 to the power of 6. And let's see if we can work backwards with another couple of ones. So let's try another one. So let's say we had 81 on this side, and we had 3 to the power of x here. So at first we look at this and we're like, well, we don't even have powers on both sides. How can we go about doing this? But 81 is that special square. We've got a square number here, so we know that it's at least going to be 9 squared, isn't it? So now we have 9 squared equals 3 to the power of x, but these still aren't equal, and we can only use our law of equality when they're equal. So we need to change this 9, and we can change that into 3 squared, but we have to put it in brackets because we're replacing the 9. And our 3 squared was squared equal to our 3 to the power of x. So now we use our power to the power rule, or as the textbook calls it, the raising the power rule, raising to the power rule. And so for this one, it's going to be 3 to the power of 2 times 2 equals 3 to the power of x, or 3 to the power of 4 equals 3 to the power of x. So therefore, x equals 4. And I've just switched them around. You could have written 4 equals x. Best practice, we tend to put the variable is equal to the constant, but it is okay to have it the other way around. So let's go back to that other one that we were working on. This one, so if we had 4 to the power of 2x equals 2 to the power of 4, we can replace the 4. So again, we're going to replace the 4 with 2 squared. So we've now got 2 squared to the power of 2x equals 2 to the power of 4. Now this is where you need to it gets a little bit tricky, because remember we're going 2 to the power of 2 times 2x, the whole thing, equals 2 to the power of 4. And then we have something equal here, so we can go 2 to the power of 2 times 2 is going to be 4x. So I'm just going to skip one line of working out and go 4x is equal to 4. And I hope you can follow that there, just because I'm out of room on the paper there. But I've just gone 2 times 2 is 4, so 4x equals 4. So therefore x, if I divide by 4 on each side, I'm going to have x is equal to 1 there. I'm going to do one more slightly trickier one where we might have to multiply out the brackets a little bit more. Let's try something like I might end up with a funny one in the end, but that's okay. Let's try, we're just going to pick a random number down the bottom, 6, and I'm going to put 2 k up here is equal to 36. Oh no, this one won't be as hard. Is equal to 36. So this is the same sort of thing. So we're going to end up with 6. We can't really do much with that, but we can with the 36. So we're going to have 6 to the power of 2k equals 6 to the power of 2. Therefore, 2k equals 2, and again k equals 1. We've accidentally done the same example there. I am so sorry. Let's have a look at let's go 8. 8 to the power of 2x plus 1 equals 2 to the power of 9. Let's go with this. So this one we're going to get a little bit trickier because we have to actually change this base into a 2. And 8 does work with a 2, but it's not squared because 2 squared is 4, 2 to the power of 3 is 8. So we're going to have to put 2 cubed in our brackets this time. So 2 cubed, and then we've still got it to this power up here, plus 1, equals 2 to the power of 9. So now this 3 has to multiply with this entire power. So we're going to have 2 to the power of 3 outside of the brackets of 2x plus 1. And this is where you have to be a little bit trickier in this example here, equals 2 to the power of 9. So we have to multiply out. Remember how we did this last year? We have to expand the brackets out. So we end up with 2 to the power of 3 times 2 is 6x, 3 times 1 is 3. So 6x plus 3 equals 2 to the power of 9. I'm just going to run to the end of another paper because we're going to run out of room. So we've got, therefore, 6x plus 3, because we've now got the same base. We've now got a base of 2, so we can use our law of equality of exponents, which is, again, technically a property, not a law, but that's okay, is going to equal 9. And now we can just solve it like algebra. So we go minus 3 from this side. Oh, we've accidentally ended up with the same solution. 6x equals 6, therefore x equals 1. I'm so sorry, I didn't try to get so many x and k's are equal to 1 in this example, but that's what we've done. Hopefully that makes sense to you. I'm going to send you some exercises with this kind of technique. We normally do it with year 10 when they're leading into logarithms, so it is an extension task, but I do think you can handle it. Let me know how you go.